Welcome to the third exercise for the lecture Pattern Recognition and Machine Learning. In this exercise, we will focus on feature extraction. We will start by reviewing the linear prediction basics, and I will do this review using the notation from the lecture Adaptive Filters. But then when we look at the three features that you learned about in the lecture, we will transfer this notation, of course, into the notation required for the features. And then we have our comprehension question section, and we will finish with a Python demo. So let's go ahead and let's get started. So we start with the signal S of n, and S of n is simply the signal to be predicted. But what do we actually want to predict? We want to predict the signal S of n based on past samples. And if we say that signal S at time instant n, this is our current sample, we can construct a case where we don't have that sample yet. So we insert a delay block, and then the output of that block is our past sample. And after that delay block, we can insert a filter with filter coefficients in H, and this is our prediction filter. And the output of that filter should then be an estimate of S of n, or in other words, it should actually be the prediction of S of n based on past samples. And like we saw in the Wiener filter, we want to see how good our estimate or our prediction is. So we look at the difference signal between S of n and S hat of n. And this is then our error signal, E of n. And in many applications, we actually use the error signal itself. So we introduce another filter, which is the prediction error filter, which directly gets us from S of n to the error signal E of n. And if we want to have filter coefficients for that, then those we can put in H tilde. And this vector is constructed by a leading 1. And the other coefficients are just the negative of our prediction filter coefficients. So H tilde represents our prediction error filter then. And like I said when I introduced the prediction error filter, we actually make use of the error signal itself in many applications. There's need to inverse the structure going from S of n to E of n. You're going to go back from E of n to S of n. So how do we do it? Like I said, we want to inverse the structure. So we more or less copy the structure up here. We insert our delay element, we insert our prediction filter, and those are the very same coefficients we used up there. But the estimate of S of n we get out of this, we don't actually subtract, but we add them here again, because up there we subtracted, here we need to add. And then this entire structure is the inverse of the prediction error filter. And if you compare those structures, the prediction error filter is a pure FIR structure, meaning that the filter is an all-zero filter. And down here, the inverse of the prediction error filter is a pure IIR structure, meaning that it is an all-pole filter. Those are our structures, but we haven't talked about how we actually get to the filter coefficients of our prediction filter. Of course, we have a cost function again. It's actually the same cost function that we had in the Wiener filter. And it's that we want to minimize the expectation of the squared error signal. But the solution we get out of this is a little bit different, because we actually have a different signal model and a different signal structure here. And the solution is that the optimal filter coefficients, they equal to capital RSS and the inverse of that times small RSS at 1. And capital R is the autocorrelation matrix. And here, small r is autocorrelation vector. We look at autocorrelations here, not cross correlations. And also the difference to the Wiener filter, you remember we had our vector at 0, and that was that when we looked at the correlation, the vector was filled starting from lag 0 to lag n-1, with n being the filter length. But here, with linear prediction, we start at lag 1 going up to lag n. So this we need to keep in mind when we write down the solution. But this then gives you the solution for the coefficients of the prediction filter. Now that we have reviewed all the theoretical basics of linear prediction, we can look at some properties of linear prediction using real signals. In this demo, I have loaded a speech signal, and we can look at some properties of the speech signal and how those properties actually relate to the linear prediction filter. First of all, down here we see our speech signal in the time domain, but I will switch this to the frequency domain so we can actually get some more information there. And what you first of all see there is the typical speech structure. You have those harmonics up here, which means those are voice sounds. This is the pitch frequency and multiples of that. But then, for example, here, this is an unvoiced sound where the excitation is mostly noise-like and not like and not harmonic. So this is then the general speech spectrum. And we can actually look at the autocorrelation function. I select the autocorrelation function and I start this. And you can now actually see what the short-time autocorrelation function looks like for a speech signal here. And what you should really notice is that there's a difference between sections of voiced and unvoiced signals. In sections of voiced signals, there is quite a bit of correlation in the signal. So the main lobe is very wide, and the legs 1, 2, 3 or whatever, they're very similar to leg 0. But then when we get in an unvoiced section like here, then it's more or less white noise, like where we have a very high peak at leg 0, and then there's not much correlation within the signal. So this is just some information about the speech signal itself, but we know that actually the linear prediction coefficients, they use the autocorrelation function to compute the coefficients. So depending on what the autocorrelation function looks like in a certain frame, the linear prediction coefficients will be different. So keep that in mind. And actually, now it might be interesting to see the direct comparison when I go to a gain plot. And the gain plot is actually how much we can reduce the error power by our linear prediction filter. And here you should also notice that we can have a very high short-time power reduction in voiced segments, because there actually our correlation, we saw this in the autocorrelation function, it is very high, and we can do a very good prediction and get a very low error signal. And for example, here, our correlation in the signal is low because we are in an unvoiced segment and we're not able to predict the next sample as well, and we cannot achieve a good power reduction, of course. And this is generally referred to as the prediction gain, what we see here, but not an average version, but a short time version. Okay, we can also see that the coefficients, they change over time because we are working here in a frame-based fashion, and we can also look what the frequency response to that looks like. You also see here in blue the spectrum of the actual speech signal, and you can see that we sort of estimate the envelope of the speech signal here. And when I then look at the error signal, we see that it's actually more flat. And this means that we reduce the high energy peaks. And this also means that we actually removed correlation from our signal when we compare S of n to our then error signal. So our error signal is actually whitened compared to our original speech signal. So if I actually increase the number of filter taps and I go back to a frequency response, you can see that here I'm able to get a lot of the fine structure, and then also my error signal will be a little bit better. And I can increase this even more. Maybe let me go to 200. Yes, now we see here that our error signal has less of the fine structure of the pitch period. And of course, if I go to frequency response, we almost match the entire signal here by just our filter, and we can reverse it. Now you have enough background to go into the next section, which is the feature section. Here we look at the 3 features we learned about in the lecture. And those features were the linear prediction coefficients, LPC, the linear prediction capsule coefficients, LPCC, and the MEL frequency capsule coefficients, MFCC. So let's start with LPC. Linear prediction coefficients are basically the coefficients we just talked about in the previous section. And when we say that our LPC features, there are vector P, then this is basically just our vector H from our linear prediction review earlier. And although the information about the spectral envelope is actually contained in the inverse prediction error filter, all the information is actually already contained in our vector P. So this is all we need here to get the information about the spectral envelope. Then linear prediction capsule coefficients take it one step, well, let's say further than the LPC features. These are actually the capstrum of the inverse of the prediction error filter. So what does this mean when we say that the LPCC features, they're called CI? And then let's get the capstrum. So we have our inverse of the prediction error filter in the frequency domain. I'll use the DFT notation here with subband index mu. Then taking the capstrum is we take the logarithm, and then we perform the IDFT. And what does this then actually mean when we break it down to get the connection directly to our LPC features? So let's write down again the first part, the IDFT and the logarithm. We can break down the spectrum of our inverse prediction error filter in 1 divided by the DFT of a certain vector. And that vector is the coefficient vector of our not inverse, but just the prediction error filter. So it's a leading one, and the rest of the coefficients is minus our LPC feature vector. And of course, transpose, because we usually look at column vectors here. And this is then everything you have to do to get from LPC features to LPCC features. And of course, you have to do a lot of computations here, and you learned about a efficient method, an efficient and recursive method to get those capsule coefficients. So in this efficient version, we don't have to go to the frequency domain, but we directly compute our capsule coefficients from our regular prediction coefficients. And we have 3 cases. One, when our index of our features is smaller than 1. Then the next case is when we are with our index between 1 and n being the prediction order, of course. And then we have all the other cases where our I is, of course, greater than our prediction length. We say in the first case, our features, they're 0. Then in the second case, we start with the prediction coefficients, but the index is decreased by 1. And then we have a sum. And this is actually a recursion, because this is a sum. We sum from k equals 1 to I minus 1. And we sum over the k we're using right here. And it's recursive because we're using ck. And we're also using prediction coefficients. And we're using prediction coefficients of index I minus k minus 1. And we have to normalize this sum by our index I. And then our third case is actually exactly that sum, but because we've ran out of prediction coefficients, we don't add the sum to a prediction coefficient, but it's just this very sum. So it's just the second part of the line above. Okay, this is then everything you need to know about LPCC features. When we look at MEL frequency capsule coefficients, this is actually then a feature that is not really based on a cost function, but it's more a method where you're aiming at something specific and we have some certain steps that we take. And I want to walk you through those certain steps. And the first step, or I want to say 0 step, is winning our signal. Usually we assume that we have already a section of our signal for a DFT, but here you can play like always with the window function. So this is sort of optional, so that's why it is 0. And then, like I've already said, the first step is performing a DFT, so we go into the frequency domain. But with MFCCs, we're looking at power. So we're then taking the magnitude square of our DFT values. And then we compute a MEL filter bank or MEL subbands. What this does is that we try to mirror the human perception, so the human auditory perception. We also perform a smoothing and a compression of our features. Then the fourth step is that we take the logarithm. And our fifth step is then actually that we perform a discrete cosine transform. And this has two general purposes. We actually perform a decorrelation of our features. And we can, this is optional, also do a compression, so we go down in dimensionality. So these are the steps you need to compute the MFCC features. In the comprehension question section, I want to now focus on the MEL filter bank. So the question is, what is a MEL filter bank and how is it applied to a DFT power spectrum? First of all, what is the MEL frequency scale? So MEL frequency scale, it takes into account the frequency resolution of the human auditory system. Humans, they're actually able to hear small deviations in frequency better in low frequency regions than they're able to hear those small deviations in high frequency regions. So this is what the MEL frequency scale takes into account, and it takes that into account by applying a nonlinear transform going from the regular frequency scale in Hertz to the frequency scale in MEL. So if we say that our frequency scale MEL is M, then we perform this nonlinear transform by taking the logarithm of our frequency. We have to, because it's a convention, normalize it by 700 and we add 1. This is then our nonlinear transform, but we also have to scale it. We scale it by 2595. And because we want to take care of our dimensions, we multiply it by MEL because we want to have MEL as our output. And we have to, of course, cancel out the Hertz. So we add Hertz down here. So this is then the entire mapping function to go from the Hertz frequency scale to the MEL frequency scale. And you can see here on the right what this mapping actually looks like. On the first axis, I've plotted frequencies in Hertz, frequencies from 0 to 8000 Hertz. And of course, then on the second axis is the frequencies in MEL. And you can see by the blue line what our mapping function then looks like. And from this here, actually, we can derive one version of a MEL filter bank. And there are several ways to do this. I'll show you one. And filter bank usually means that we don't work with all frequencies, but we combine frequencies together. We're just working with frequency bands. So that's what we're doing here. And we design it by specifying the frequency bands actually in the MEL frequency domain and not in the Hertz frequency domain. So we can define our center frequencies of our subbands. And we can just say, okay, let's do 5. So I can put my center frequencies here on 500, 1000, 1500, 2000, 2500. So I want to have those equally spaced in the MEL frequency domain. And now I have to know what those correspondences are in the Hertz frequency domain to know what I actually have to do in that frequency domain to apply the MEL filter bank. So I find out the correspondences by doing this here for 500, 1000, 1500, 2000, 2500. So those are my corresponding frequencies then in the Hertz frequency domain. And if we say that we want to design our MEL filter bank using triangular filters, then I want the peak of my triangle to be on those center frequencies. So I can mark those 5 frequencies here. That's where the peaks of my triangle should be. And if I say that I want to have a 50% overlap, then basically those center frequencies, they're also starting points or ending points for other triangles. So I copy all those down here as well. And then I can just do some connecting of those points. So if I start with the first subband, let's do that in orange. Then this triangle, this will be the filter for my first subband. And then I can go on with the next here in yellow, second subband. Then in light green, third subband, dark green, fourth subband, and then the last subband is then blue. But what is also important here is that I apply this filter, I have to multiply it with my DFT power spectrum. So I actually have to define it over all subbands. Here, of course, I have the subband indices on the first axis. So wherever I have not marked here the triangle, this filter or this vector later on, it has to be 0. So let me just mark this here. So this part has to be 0, then this here to the left and to the right has to be 0, and then again to the left, to the right, it has to be 0. And once we end up with our last subband, only the left has to be 0 of that triangle. And this is then how we get our triangles for our MEL filter bank. And of course, you saw in the lecture that there is a version where we normalize them. So actually the peak height would decrease when we go to the right on our subband indices. But this is, you're quite flexible in how you want to design it. And here I just chose this version because it's easier to derive basically. But when I would go to the application, I would actually normalize those triangles by their area or by the number of subbands on the Hertz frequency scale contained in them, and I would normalize them by that number. But here, we'll just stay with that. And the question that remains now is how do we actually apply those filters to a DFT power spectrum? Because for now, we've just drawn some funny triangles, basically. So about the application. Here in this example, we have 5 triangles, 5 filters, and 5 subbands. So we say nMel equals to 5. And you can see here, because I plotted this on the right bottom, that I wanted to work with 128 subbands in the DFT domain. So I just say that n sub is equals to 128. And those numbers are just an example, basically. But this is what we have drawn here on the right. And you know from the lecture that actually your subband vector on the MEL frequency scale, it actually equals a multiplication of a matrix M times the vector you want to transform. And just so you understand what we're doing here, let's look at the dimensions. Our vector YMEL, that should be, of course, a column vector, and it should have nMel entries because we want to have nMel, or in our case 5, subband values. And then the matrix M, it should be of size nMel times n sub, which in our case here would be 5 by 128. And it has to be n sub in the second dimension because we multiply it against our vector in the DFT domain, which is of course of length n sub. Now let's look at our matrix M. So our matrix M, as we saw when we looked at the dimensions, it has, in our case, 5 rows. And in each row, we have the coefficients of our individual subband filters, our differently colored triangles here on the right. So we basically have to put those coefficients in here. And if I wanted to start with the first subband in orange, it would be the weight of subband 0 and the first coefficient, but I start here of course with 0 as well. So W00, 0, and then I go on to some coefficient index I, which is the last non-zero coefficient, and I fill it up with zeros. And when I go to the next subband, I start with coefficients that are 0, and then at some index k, I will have non-zero coefficients. So I will have W of subband 1 at index k, and I will have non-zero coefficients up to, let's say, index L, and then I will fill the rest with zeros. And that's the same for the other two subbands that follow, and then the last subband, I start with zeros, and then at some index R, I have non-zero elements, and I go up to coefficient 128, which is of course index number 127. And here our very last index is, well, it could be 0 or non-zero depending on how you end your triangle there, but we don't fill it up with zeros back there because this is our last subband. So you can see here that we have a bunch of zeros in our matrix, and we only have some coefficients that are not 0, and we want to take certain DFT subband indices into account when we go into the Mel frequency domain in that specific subband, so that when we do the multiplication of the matrix with our DFT vector, we combine the right frequencies with the right weights to form our subband Mel frequency values. Now let's go ahead with the Python demos. There's one demo for the computation of linear prediction coefficients, and there's another demo for the transformation of linear prediction coefficients to the capsule coefficients. So let's go ahead and let's get started. For both demos we're working with artificial signals. I created a white noise signal, and I created a inverse prediction error filter. And I used those filter coefficients to filter the white noise signal, and the result was the colored signal that we load here. And we're working with both the white noise and the colored signal here in this demo. And the first thing we do is we plot the power spectral densities of those two signals, and we will see that, of course, the colored signal is colored and the white noise signal is flat in the power spectrum. And then we will go straight into the implementation of the computation of the prediction filter coefficients. We're computing a filter of length 5 here, and the first thing you need to do is estimate the autocorrelation function, because with that you can compute the autocorrelation vector and the autocorrelation matrix. With those two quantities you're able to compute the optimal prediction filter coefficients. And because we want to compute the error signal, you then also need to compute the prediction error filter coefficients. Those you can then apply to get the error signal, and once you have that, the rest of the script will be executed. The error signal will be plotted, the power spectral density of course, and we will see what effect our filtering had on the colored signal. So if you want to implement this yourself, please pause the video now, as I will now walk you through the implementation. For the autocorrelation function, we again introduce the variable correlong, in which we put the output of the convolution function, and we convolute the colored signal itself, but of course with the flip version of itself. This thing gives us the long version of the autocorrelation function. And to get the actual function, we take only the second half of that, and we put those in core. And then from that, we can compute the autocorrelation vector. Remember that this vector starts at lag 1. we don't take the first value of the autocorrelation function, we start with the second one and then select n values. The autocorrelation matrix, here we apply the tuplets function, and we select element 0 up to n-1 from the autocorrelation function. Now the solution is just that we multiply the inverse of the autocorrelation matrix with our autocorrelation vector. So we use NumPy's matmul and NumPy's inverse function. We apply the inverse function to R, and we multiply the inverse with small r, and this then gives us the optimal filter coefficients. The prediction error filter actually uses the coefficient of the prediction filter. Remember that we just add a leading one, and then we take the negative of those, so we can use NumPy's append, with the first parameter being a 1 and the second being our prediction filter coefficients, which of course we have to negate. This is the prediction error filter. And this prediction error filter we can apply to our colored signal. We use the convolve function again, so we convolve colored with HE. And of course here we want to take only the first L values here, because remember the convolution output is always longer than the length of one individual input. So this was it. Now let's go ahead and run it. You see here the signals before we apply the linear prediction filter. In orange you see the white noise signal, and as expected the power spectral density is almost flat, there's no coloration there. And then in blue is the colored signal. So remember the colored signal was produced by applying an inverse prediction error filter to the white noise signal, and you clearly see here that the signal is colored now. So what happens then if we apply a prediction error filter to the colored signal? This we see here then with the green line, and you see that this is now more or less identical to the white noise power spectral density. So we were able to remove the coloration. So we were successful with our linear prediction approach. And this also worked because I selected n equals 5, which was exactly the length that I simulated the signal with. But now let's set the filter length maybe to 3. We can just change it from 5 to 3 here and then run it again. And now we see that we don't have enough coefficients available. We don't have enough zeros or poles, however you want to see is to model. And we're not able to remove all the coloration that is in the signal. But with n equals 5, we were successful in removing all the coloration from the signal. Now in the second MO, we will look at the transformation from the linear prediction coefficients to the linear prediction capsule coefficients. And we will actually do both versions. We will do the straightforward solution and the efficient solution, and we will compare them. So let's look at the script and what we have here. First, I'm loading some coefficients. Those are the coefficients that I used in the previous demo to create our signals. So those are basically our true linear prediction coefficients, and we're just using them as if we had estimated them. And then the first section is really that we just plot them so that when we run the script, we see what those really look like. Okay, and then we know that we actually need the prediction error filter. So I want you to create the prediction error filter or that vector. Then we go into the frequency domain with our FFT. Then we want to actually, because we now have the prediction error filter, we need the inverse prediction error filter. So we need to compute that. And then we can actually compare the spectra of the inverse prediction error filter and the prediction error filter in the frequency domain. And you should see that they're inverse of each other. And then we do the actual transformation to the capsule domain, so with logarithm and IFFT. And this is then basically the straightforward solution. And then the next part is that we compute the recursion, and we do some preparation here. And then we go into our loop, and I've already completed the first case for you, and I've prepared the inner loop for the sum in the first case and in the second case. So you need to basically compute the sum and then add your prediction coefficient, or in the last case, don't add it. So this is basically where you have to implement the recursion. And then the last is that we plot both the solution with the regular just IFFT or DFT and the efficient version. And of course, we hope to see that they're more or less identical, except for maybe some numerical errors. So let me walk you through my solution. Okay, so let's start by creating the prediction error filter. And as you know, that starts with a leading one. So we just create a variable that is just NumPy array of 1. And then we can use NumPy's append function to append our prediction filter coefficients, but with a -1 multiplied against them. We've already got the DFT of our prediction error filter, and to get the inverse prediction error filter in the DFT domain, we can just say it's 1 divided by P. And then if we want to go to the Kapslor domain, we have to first take the logarithm of the inverse prediction error filter in the frequency domain. So it's NumPy's logarithm of that, of P_inf. And then of that, we have to take the inverse DFT, the inverse fast Fourier transform. And that's then already it for the straightforward method. Then when we go down to our efficient recursion, we can jump right into our second case. And we first have to compute that sum that you see in the recursion. So we use the same variable to increment basically that sum. So we say that a variable crec of I equals to crec of I, and then we add something to that, and we add crec of k times k, which is of course our running variable in this inner loop, times our prediction coefficient of index I minus k minus 1. So this is then our sum, and you know that we have to actually normalize it, so it's crec of I equals crec of I divided by I. And in the second case, we actually add a prediction coefficient, and we use the prediction coefficient of I minus 1. And actually, the third case is very similar. So let me copy it down here. So I copy the sum down here, and I copy the normalization down here. And in this case, we do not add a prediction coefficient. So I just delete this here. And this is then already the finished recursion. And we can go ahead, run the script, and look at the results. Here in this plot with the coefficients, I just wanted you to see that nothing funny is going on and that we have a total of 5 coefficients in our prediction filter. Now, when we go to the spectra that we plotted, we see that we did the calculation correctly and that the inverse prediction error filter is actually the inverse 1 divided by the prediction error filter. So let's look at the result that we're actually interested in, the comparison of the two computation methods. And you can see here that the blue line follows, in most cases, exactly the bullets of the stem plot. In some cases, we have some slight deviations, but we can say that they're more or less numerical nature. So you see in one method we go through a DFT, an IDFT, a logarithm, and the other case we don't. Mathematically, they're the same, but numerically, they're not. So that's where some of those small deviations can come from. But overall, we can say that yes, the derivation in the lecture was correct, and that efficient version of the computation for the LPCC features, it can certainly be used. That concludes this exercise video. Thank you for watching.